It's a simple server with a thread pool, a couple of mutex locks surrounding it, and a conditional signal accessing the hard drive and backwards. The implementation introduction. When multiple clients ask for your resources simultaneously in order to conveniently and efficiently provide them, you need to solve a delivery problem. Most modern web servers use multithreaded to economize and maximize efficient use of their resources, making it possible to distribute resources adequately and concurrently for thousands of users, allowing us to have unprecedented connections, banks, tax filing, vaccine distributing, census, not to mention the immediate access to academic and medical information. My project is to exemplify the classical multithreaded server implementation that allows us to maintain conveniently connected. The implementation, the client sends the file name and the server then reads the file name and sends the contents back to the client, emulating how a web server works, but without the HTTP parsing. And current implementation does not have an access control list, allowing to read anything on the hard drive. Timed comparison of a simple server for demonstration purposes only, with multiple threads, using the simple server to call the server code from /temp/test files, having copies of the server.c file 1 through 5.c, and having 6.c being 10 times the size. The simple client requests the page. Here we have our simple client in Ruby, having the local host on port 8989, actually getting the time elapsed and writing on here's where it's getting from the /temp/test files. And our multi-client tester, it's a script that runs that previous Ruby client, but multiple times. We're gonna need to allow a backlog of more than one in the server, also to allow this sequentially. And we're gonna run it sequentially, requesting one and multiple files at once. Multiple clients take more time. Here we can see, right, and on the left is the individual clients. So let's do something about it. Let's actually make it pthreaded. Let's do a # includes pthread.h, and we're going to need to instantiate our thread, keep track, and provide a thread function, handle underscore connections, and argument. Change the handle connection. Change the handle connection because the thread functions need to return a void pointer. And not forget to return null so the compiler doesn't show errors. Running it gives us about the same time as before, so we need to modify our tester to give us each request round robin style, to see better what's going on. So we can see that some requests are taking longer, and these are the bigger requests. But in customers, when done sequentially, you can really see the slow connections cause the rest to start delaying. Here on the right, left 0.2, then the next one's 5, and they start delaying. All right. Multiple connections are taking about the same time, but now they're taking longer than when done with threads. Slow connections, bigger file causes delays on the other connections since they have got to wait. You can really see the difference if you have access to a slower magnetic disk or another server, or anything slow that doesn't tie up the processor. Asleep 1 to emulate this situation. In this example, you can see how sequential calls lag behind while multiple threaded thrive. Flood connections. If we flood the connections, it has one thread per connection, which slows down the server. Each thread is taking memory and CPU time. At some times you have got to mediate, not to slow down your system. We're going to help it out with a thread pool. Start the thread pool with the size and declaring the array pool of threads. We create our threads. Then we're gonna have to find our threads because we want to reuse those threads, not just let them terminate. And input connection information on a queue so the threads can query this and find. Add the connection to the queue and maintain the thread in the loop. And we have comparable performance, but the second time that it's run, it actually runs into a race condition, so it's not thread safe. What happens is if one of the threads starts desynchronizing or finishes earlier and the other one's still working, it starts desynchronizing, so the other one asks already for the next resource. So what we have to do is make a way so they are synchronized and like they don't get or they don't ask for one of the other. So we're gonna ask for a lock, and that way they keep synchronized, and they're not gonna take the other thread's work and get out of sync, thinking the other thread that is going on the pairs, etc. We're gonna sandwich the locks right before and after the queue, lock and unlock, and pass the mutex. Working the Mutex Locks multi-threaded server slow now for locking and unlocking, but we have a multi-threaded server that is up and working and not crashing, but it's still hogging CPU resources. CPU cycles and the way to work. Having your thread checking all the time if there's work to be done in the queue is not effective for its users. All the available CPU cycles. Trade-off between CPU overhead and responsiveness. More responsive, shorter sleep time check. Queue more often, uses more CPU. Less responsive, longer sleep times, check queue less often, uses less CPU. The pthread condition variable lets a thread wait for a signal, not unlike a semaphore, for it to effectuate some work, and are here implemented to allow the thread to wait for the process and not use all available CPU cycles. Condition variables are designed to work closely with Mutex locks, and therefore that's why you have to send the Mutex when you wait, because when you wait, you also release a Mutex lock. Pthreads are stateless. Threads are waiting each time for the loop, and main thread is signaling each time a new connection comes in. But when we have many signals, we can see a flaw. When it calls wait, it waits regardless of how many times it has been signaled before. It just waits. If threads aren't keeping up at some point, there is no new work added to the queue, so signal isn't being called anymore, but there is a lot of work still on the queue, and worker threads are finishing the task, and they call wait, and they wait. When many connections come, you can see a trouble. It gets stuck. To fix this, you need to call the queue, and if it returns no when you call, wait on your conditional. So we have a working Mutex Locks conditional variable triggered server. We ended up with our working multi-threaded server using thread pools that doesn't run into race conditions, stacking a bunch of threads, and that does not use all your available CPU cycles, making our server attempt to deliver a decent service regardless of how big the request or small delays here and there. Thank you. Any questions? Please. Thank you for your time.